to drag to the right window. Yeah, cool. So thanks for having us. I'm obviously James from EDINA, and I'm going to talk to you about how we use Python for geospatial data processing and service delivery at EDINA. So I'm going to give you the slides about EDINA and the UK Data Service. So EDINA, we're based at Edinburgh University, and we provide 3 core services: Notable, Elm, and Digimap. And these are services we sell to higher education institutions like Edinburgh University. Notable is a computational notebook service, so it's like Jupyter Notebooks and RStudio as a service. And we provide value around that, so we have various Docker containers for different Python libraries. And it also includes a thing called NB Grader, which allows a lecturer to set a course materials in a Jupyter notebook, and the students can fill in those notebooks, and then it can be assessed, so they can do their courses online. And then Elm is our latest thing, which is the AI innovation platform for education. Elm stands for Educational Access to Learning Models. So through the Elm platform, you can access OpenAI, and also we've got some of the Meta 4, I think, the Llama 4 LLMs. And then Digimap is our core geospatial service, which provides access to a lot of different types of data collection. So Ordnance Survey data, British Geological Survey data, historic map data, and census data, and agricultural census data. So census data is like information about people. Agricultural census data is information about animals or livestock. And the 2 Digimap services I'm going to cover today in my pipelines that I'm going to talk about are Digimap census for humans and agricultural census for the animals and the people. And then the 4th thing at the bottom here is the UK Data Service. And this is EDINA is part of the UK Data Service, along with 3 other institutions, University College London, Manchester, and Essex. And this is social science data. And unlike the top 3, it's an open access service. We don't sell this. This is funded by the Economic and Social Research Centre. And we provide basically access to social science data and census data. About me, so I've been using Python since 2.3, which is about 20 years ago. I first used Python because I wanted to load some geospatial data into MySQL, and I was having problems. I work in the EDINA operations in our data team, so I'm not a software engineer myself, but I have to work with software engineers on an actual service. I use Linux, Python, Postgres, and SQL. I tend to do as much Postgres and SQL as I do Python. And I use Python to charm my Postgres database and create MySQL and run stuff. And I do a lot of geospatial stuff. And I write a lot of spatial SQL to do my geospatial analysis rather than using a desktop GIS. I don't know if people know what a GIS is. It's called a geographical information system, and it's a way of manipulating spatial data and running analysis and creating maps. But as a Python person, it's much more to do that automatically using code, so that's what I do. And I say, if you take Python, you take SQL, you take Postgres and PostGIS, you get a geospatial superpower, and you do pretty much everything. So as I say, how we use Python at EDINA, all our services written by the software engineers are written in Java, and we use TypeScript, use Angular to do all the front ends. And what I actually do in the back end is we use Python for data science, data engineering, and analysis. So we can't use Python everywhere, but unfortunately. And that's just because the way we've grown up over time as a company, it was all very Java-based. And so this is what I use at EDINA for my Python environment. So pretty much probably the same as a lot of people. I use PyCharm. I don't like Conda, so I use PyEnv to do my versions of Python in my virtual environments. And I use PyTest for test my code. And I use SodaCore to do my data testing. I'm going to mention SodaCore later on because we use that as part of our pipelines to test our data sets. And these are some of the Python libraries I use. These are the non-spatial ones. So I'm sure plenty of people have used these as well. So we've got requests, which allows Python to interact with the web. Beautiful Soup allows us to troll through HTML and find stuff on the web. Fabric allows me to execute stuff across different VMs. Click allows me to build a command line interfaces to Python programs. I prefer Click to using argparse and stuff because I just find it easier to use because you can just decorate all your functions with like the clicking library, and it's very quick to create nice documented CLI programs. I use Jinja templating because I find that templating solves an awful lot of problems when you're using Python. You can use templating to create random system files or write SQL or write HTML. I find it gets me out a lot of problems quite easily. And I use Postgres as a library rather than CycloPG2 because again I find it easier to use and I find the API better. And then I use pandas because like everyone else to do data cleaning and manipulation. And then geospatial data is, I don't know how many people are familiar with geospatial data, or maybe, so essentially it's a way to model some aspects of the world. And there's two almost branches of geospatial data. There's vector data and there's raster data. So vector data is essentially features, so point, lines, and polygons. And you have some attributes attached to that, so that it could be a building, and you could have like, the number of floors, the type of building it is. And raster data is essentially like a digital image, but instead of each cell having like an RGB value, it could be like something like the height of the Earth, or it could be a radiance value from a satellite image, or some sort of like environmental data set. And then within geospatial data, we have all these different types of themes related to it. So the data is always located in some place in the Earth. So we have like different types of spatial reference system. And we have a variety of data formats. These are just free. There's like endless numbers of geospatial data formats. And we have a thing called, we can take Postgres, and PostGIS provides a geospatial extension to Postgres, which gives you different types of geospatial data type and also functions that will then run on those data types. So again, you can do stuff in Postgres and write spatial SQL without having to go near a GIS. And then these are sort of geospatial Python libraries that you can use against those to manipulate your geospatial data. So there's a holy trinity of Fiona, Shapely, and Rasterio, which tend to get used quite often together. So Fiona gives you the ability to read and write vector data, and you can manipulate the features. Shapely allows you to do spatial analysis on those geometries, so you could compare two polygons in space. You could tell, is this point within this polygon? And then you can edit the actual feature geometries of the polygons. You could add more points or break down line down. And Rasterio allows you to do the same for raster data that you do for vector data with Fiona, or Fiona, yes. And GeoPandas adds to Pandas the ability to consume geospatial data. So in Pandas, you get a series and a data frame. With GeoPandas, you get different data types. You get a geoseries and a geodata frame. So you can do similar vectorized operations in GeoPandas that you would do with geospatial data that you would do with Pandas. So you can aggregate data and clean data and stuff. So that's a nice way of using geospatial data. And the talk's in 3 bits. The first bit I'm going to talk about how we use Python, the UK data service. And then I'm going to talk about 2 pipelines for Digimap Society and Ag Census. So a bit more about the UK data service. We specifically provide help with the census support service. So the census data, oh God. Oh. Yeah, maybe not do that. So the census is collected every 10 years. What you see, in the past, they used to send the paper form out to every household, and you'd have to sign up various things like how many people live in that house, the age of the people, the age of the children, what sort of job you do. And then the census agency gather all that information together and run analysis and then produce actual census data, and that's produced at distinct types of geography. So it could be the council area of Glasgow all of Scotland, or a particular ward or a district, and that gets done every 10 years. So it's normally 2001, 2011, 2021, except in Scotland, where the census was done in 2022 because of COVID, so it was like 1 year late. And in order to map that census data, they produce these digital boundaries, which are the representation of that geography on the ground, so the council area boundary, or the ward boundary, and the district boundary. And at EDINA, we create applications that allow people to download those digital boundaries so they can then join their data to those boundaries and do mapping and spatial analysis. And we also provide these things called geographic lookup tables, which allow you to make a cross-referencing from one geography to another. So you could go from a council area to a country, or from a postcode to a ward, to a district, to a sector. And that's quite important if you've got survey information which you want to relate to other types of geography. And we hold all our stats and boundaries inside a PostgreSQL database. And so this is our EDINA service called the UK Data Boundary Data Selector, and this allows users to download boundary data. And although the app is built in Java and it's got a UI, a JavaScript front end, we've got Python behind the scenes doing the actual ETL. So that's the extract, transform, and load. And we have a similar application for the postcode data. And this allows users to download sets of postcode data from things which are called a postcode directory. So a postcode directory provides a single record for every postcode in the UK. So that's about 1.3 million records. And so behind the scenes, we use a command line tool called OGR to OGR from an open source package called GDAL. So GDAL is the Geospatial Data Abstraction Library. It's an open source C++ library, which provides access to different types of geospatial data formats, and you can do operations on it in C++, like spatial geometry. You can test this geometry is related to this other geometry. And as part of the GDAL package, they provide a command line program called OGR to OGR, which is great because you can connect to a Postgres database and then output types of your postcode records or your boundary records in different types of geospatial data format. The command line tool is quite scary in terms of the help page. It's got hundreds of arguments and different ways of using it. It's extremely flexible. And so what EDINA done, we've created our Python wrapper around the OGR to our command line tool. And we use that. So we've got an OGR converter class, which wraps the OGR to our tool. And then we have two subclasses, which use the OGR converter tool specifically to service those requests for the boundary data or the postcode data. And so our Java app comes along, takes the user data into stuff from the front end, passes it to our Python library, which checks everything's correct, runs the OGR to our command line tool, and it spits out a boundary or a postcode. And then the Java application takes that data on the file system and packs it up into a zip file, which then gets presented to the user. So that's how we have Python inside, amongst all the Java and the UI and the JavaScript. I think I'm moving out of frame. And for our internal use, so within my team, we have to update these postcode data and boundary data quite a lot. So we've written command line tools in Python to make our jobs easier and automate stuff, so you don't have to silly manually load stuff into Postgres. And I like command line tools because they're great to make changes. Rather than to generate a UI, you can just add a new Python function and then decorate it with your click stuff. And you can also integrate your command line tool into other workflows very easily, and it's also great just to create a throwaway script, just run the tool, do some data update, and then away you go. And so we've got like a boundary manager, which we use to upload the boundary data selector. And this is all written in Click, so you get these nice Click style help documentation when you try and run the tool. And we have a postcode loader tool, which does the same for our postcode data. The boundary data tool will run like daily, multiple times within a week. When we get a new data set we have to load, the postcode data tool will be run every 3 months when the ONS, the people who provide the boundary postcode data, requires to do a data update. I'm now going to move away from the UK Data Service and look at how we use Python to build our pipelines for the Digimap interfaces. So the first one we're going to look at is Society Digimap. So we have a map of census data. This is showing census boundaries. And this is showing the percentage of households in each area that live in semi-detached homes. And this is for Glasgow. So as you can see in Glasgow City, most people don't live in a semi-detached house, whereas they do in the suburbs. And this is 2022 Scottish census data. And so we have a data pipeline written in Python that allows us to do all this loading of the data. So we obtain the source census data from the National Register of Scotland, the Office for National Statistics, or NISRA in Wales. We do a clean catalogue and load operation. We construct the map area we want to map, which could be that percentage of households within a certain area. We do aggregation of that data to different levels of the geography, so from the smallest output areas, which they call them, up to wards, counties, districts. We do some normalization, so we're not presenting the raw numbers. We're doing it as a percentage of a population or number of households, so that it's comparability. So you can compare Glasgow, Edinburgh. If it wasn't normalized, it would have no sense. I do some quality assurance, and then we build the actual chlorophyll maps and generate the web map and the UI config for the Java apps. So this is what some source census data looks like. It's a big spreadsheet. Down the left, you've got the unique geography IDs and a bunch of variables. We do basic Panda stuff to the source data. We do like a replace a lot of numbers with like from dashes to zeros. We do some cataloging. We assign some aliases to the very lengthy column names, because Postgres has like will complain if your columns are like larger than 64 letters long. So we assign a nice short alias, and then we just use the pandas to load into the SQL database. And I use Jinja SQL templating a lot. I don't use an ORM. I just create all my SQL as Jinja templates. And then so when Python's interacting with SQL, I can just call the template, give it some context, and yeah. And if you've not seen a Jinja template, that's what a Jinja template looks like, so shown from SQL. So we can pass in like the mapped columns, and you can have like a for loop to loop through them and create our SQL. And this just creates a table, but I have like some of the SQL for the operations we're doing can be quite large. So. And then, because it's a data pipeline, we want to make sure, and we could be not sure what transformations we're applying or what state the data is in. I write to like data quality tests. In the same way, you write code tests to check your code. You write data quality checks to make sure your data's okay. So this is what a SORA data quality check looks like. You write it in YAML for things like all the columns are present in the table. You can check the number of features, and you can check that the values are in a certain range. Again, I started using SodaCore because I tried to use a thing called Great Expectations, which does the same sort of thing, but I found Great Expectations really hard to use. So I went back to using SodaCore because I found it was a lot nicer. And then we have a data classifier. When we're building those choropleth maps, we have to take, there's 40,000 values of number of households, and we have to collapse that into 7 like map breaks. So, and we use a Python library called mapclassify to do the classification, and Palatable provides our color amps for the choropleth map. So again, some simple Python code where we're using a SQL database into a data frame. We're applying a map classify operation. So we're classifying the flat column, and we're telling it how many classes to use, so 7. And what we'll get back is a list of the lower and upper bounds for those class breaks. So from say 0 to 100, so 0 to 100, 100 to 200, 200 to 300, 300 to 400, 7 times, 7 colors. in a sequence from yellow, green to blue. And then when we're generating the actual maps themselves, we use a piece of technology called map server and map proxy. So map server serves maps from Postgres databases. It comes with its own domain-specific language that you use to tell it how to draw the maps. So you can plug in, tell it what database to hit and how you style those maps. Again, I use a Python template because I don't want to have to write the domain-specific language myself, because they, again, can be quite enormous. So I template those in Jinja, and I can do that from Python. And then map proxy is like a map caching layer. If you've used something like Google Maps, it has these like, and you use one of their Sliffy map things, it basically builds a map from lots of little tiles. And so that's hitting a map cache. And that's what we do. We generate basically sets of small tiles for all our maps, so that when the user requests, it's not generating the map there and then, it's just using a cache. But map proxy is configured using YAML, and YAML and Python go together nicely, so that's quite easy to generate. And lastly, the digital application I'm showing you itself, the Java app, has a massive big XML file. So again, we use templating to write that. Going backwards. And then, so you can see we can shove different types of different variables from the census data through the same pipeline, and we end up with different maps in the UI. So Glasgow, and then we've got sunny air down the coast, showing unemployment. So in air, there's worse unemployment north of the river than south of the river. And we do a similar sort of thing. We have the same sort of pipeline for one of our other digimap collections called Ag Census, and this provides agricultural data, but instead of shaded polygons, we've got like shaded grid squares. The reason we use grid squares is it provides a consistent geography. So you can look at the same grid over different years, and the grids are all in the same place, so you can do like change analysis. Whereas you use polygons, the polygons are of a different shape depending on the year, so it's a lot harder to compare the same like for like. And again, we have a similar pipeline, so we get the data, we do some cataloging and loading. This time we do some slightly different spatial operations. We do a thing called asymmetric mapping, where we basically use some land cover data and we do some interpolation to a grid. And because the data is sensitive, because it's being provided by farmers for an annual survey, we have to apply something called disclosure control, so that we remove the potential to reveal the identity of individual farms. And again, we generate some web mapping UI config. So, and this is what the source agricultural census data looks like. This data is sensitive, so I've had to blur it all out, the actual values, but you can see it's the same sort of structure as the census data. You have a bunch of geographies and a bunch of headers, and that's where the Llamas in the title comes from. It's nothing to do with metaphor or like LLMs. It's actual counts of llamas from the agricultural census. So asymmetric mapping. The agricultural census data comes by parish, which are these red polygons. And we want to assign, as part of the analysis, only areas where there is actual agriculture could fall, which would be like a field or an area of upland. So in our PostGIS, we do a spatial overlay for the red polygons against a land cover model, which is coming from satellite data. And that's what this map's showing here. So on top of the red polygons from the parishes, and below you've got two classes of colour. You've got purple areas and green areas. This is near Edinburgh, so the purple areas are like the Pentland Hills, where you don't expect to find sheep farming. And the green areas are areas of fields where you get like higher quality fields, like growing crops or possible dairy farming. And the areas of white are areas where you wouldn't expect to get any agriculture whatsoever, like the city of Edinburgh or lakes or the sea. So we take all that agricultural census data by parish, and then we create a subset of polygons on only the areas where agriculture could actually be found. and this is very more simple Python. So we're running a spatial select inside PostGIS, rsdbl.sql, and we're using the Fiona geospatial library to write that result set to a shapefile, because we're going to use it a shapefile as a type of geospatial data. We're going to use that shapefile later on in the analysis. So that's what we're doing here. We've got some Postgres result set, and we're walking through the geometries and writing a set of features of the geometry and the land cover type and the agricensus variable. And then we're going to do some spatial interpolation of the final data set to convert from a set of vector polygons to a raster grid. And unfortunately, Python's great at some things, but it's not always great for spatial statistics. So we have to use R to do that. And in order to use R, we run R inside a Docker container, which Python will then call, do the R bit, and chuck out the output, which will then feed the rest of our Python process. So again, we use the Python Docker library. We've built a local Docker image that has RStudio in it, and it's got our script in it. We check the container's running, and if it's not running, we run it. So it's in the background. We do sort of mount a folder. And then we have some Python that executes the Docker container and runs the R script. We pass it our input shapefile, and it spits out a raster. And then the final thing we have to do is disclosure control. So when the raster gets produced, it's got a spatial resolution of 250 meters. And these like F1, F2, and F3, they're individual farms. Conceivably, you could have a case where a single farm falls within a single grid cell, and that would be known as disclosive, because you could then tell that that farm only had was the only person growing llamas or had a certain type of crop. And you don't want to really do individuals as part of census data, because it would be bad from the farmers, because then the competitors could tell what they were doing and stuff. So to avoid that, we have to apply these things called disclosure controls. So the output data provided to customers is always a lower resolution than 250 meters. It's either 2 kilometers, 5 kilometers, 10 kilometers, or 20 kilometers. So in the case here, it's more ambiguous about what the underlying data, which farm the underlying data came from. And we do that using this Python RStudio library, which does for vector data what we do for raster data. And again, the output of our pipeline is we get the data shown in Vigilant UI, this time at 3 different resolutions, from low resolution up to high resolution. And the resolutions the data is available at depend on the type of variable being mapped. Because some of them, I say, like chicken growth and poultry, if you're like in competition with your neighbouring farmer for poultry growing, that's environmentally sensitive data, that's sensitive data. So you only provide that at a much higher resolution. And so some of the things to the end of the talk, I think that's about half an hour, that we're looking towards looking at EDINA, is using DuckDB as part of our operations, because we use Postgres, and there's now a spatial extension for DuckDB that lets you do the same sort of things in DuckDB as you can do in PostGIS. I'm looking at using Dagster, because I tried to use Airflow before. And I'm trying to look at using alternatives to PyN. UV comes up quite a lot. I've also heard of a thing called Pixie, which came up at a geospatial conference, which I don't know much about. So thank you for your attention, and I'd be happy to take any questions.
One question from like way back at the beginning of the slides. I noticed you said pandas. And sorry.
Settings. Here we go. I'll give you this. Speak into that.
Can you yell? Yeah, I was just saying, great talk, thank you. Also, you explained one of my questions, which was why are llamas counts like blurred out like they're like API keys or something? It's like, oh, because it's sensitive data. And so yeah, totally got it now. But yeah, it was just at first I was like, that seems weird. But no, the question was about the. From the beginning, you're saying you use pandas and I've used pandas, but recently I moved to polars. I mean, you're talking about investigating new technology stuff. Yeah. I wondered if maybe one of yours was an extension of pandas or allowed you to use pandas data. Have you looked at polars? Is it not useful with that, or is it just that you have inertia in the project?
Our source data, they're relatively small, so using something like polars or like DuckDB, for example, to do is not something I've not found problems using pandas just to clean my data set like 50,000 records in it, because I've not hit the limits. I just stick everything in Postgres and find that if properly like set up Postgres database, I've not really hit any problems in terms of like performance yet.
Thank you.
Anyone else get any questions? There we go, it's connected there, yeah. You can speak into that there.
Thanks. Yeah, I think on the polar side, I think there's no geopolars yet, but
Right.
there is geopandas, so if you depend on. But I wanted to ask, because you have Jinja for SQL templates,
Yeah.
have you looked into DBT, DBT core, which
No.
is basically
Right.
Jinja SQL templates?
Yeah, yeah.
Because it looks like you're kind of,
I sort of homegrown my own like templating thing
Yeah.
basically because I just found it easier to keep my SQL in a big template file away from my, rather than mix it on my Python, which I didn't like. So, yeah, that's something I'll look at for sure. Yeah,
I guess you're templating stuff that is not SQL as well.
yeah, I like HTML and I say the random DSL written map files and random YAML file and stuff that the actual the engineers create some configuration file to convert the map. So it's a massive XML thing, and so I'm templating for that. And I'd say I find templating just gets you out with so many problems. It's just, you can create a template and yeah, chuck some structure at it and there you go.
Any other questions? Oh, Alien, there you go. Just in the top.
Is it possible to, within, for example, a word polygon, split out groups of houses so that you had like them 200 groups of letterboxes that you could walk around?
Sorry, what do you mean?
So a ward is political geography.
Yeah, there is
So if you think of trying to deliver leaflets,
there are smaller geographies within wards.
yes, down to polling districts,
Yeah.
yes. But keeping within that,
Yeah,
that polygon boundary, be able to count off houses into the amount of houses that somebody could deliver a leaflet to in 2 hours.
you can get the individual postcodes. Yeah,
I think I've got the answer to that. You can buy data sets for individual buildings or addresses, even post boxes. But so you have to buy that as a data set and you get a point for each one.
there's also a free data set called OpenStreetMap, which provides
Oh yes, I've done this all manually.
right. Okay,
I haven't used GIS for about a decade.
right.
But yes, I used the word polygons and things like that, but
Right.
having to put it down to person walks this route
All right.
within that. And
So you're trying to like
strictly within it.
create the most efficient way of walking.
Yes,
The travelling salesman problem.
yes.
It's a classic in spatial analysis.
So
Yeah.
that bit can't be automated yet.
There are Python libraries that will do stuff like that,
Uh,
and you can. There are various like there's a thing called I don't know if you use there's a Postgres database has a thing called PG routing. Which
Oh no, when I did it, it was pretty much all manual. The
Well,
polygons
for
were the
Postgres,
only bit we got.
because like Python, Postgres is an open source thing. It has lots of libraries, and there's a library called Postgres called PG routing, which allows you to do lots of like spatial routing type operations. So you can do like traveling salesman, you can do shortest path and stuff. So if you can, so you can load like a road network into Postgres, and then you can run like a traveling salesman operation, which is kind of cool in SQL. So, or Python, which calls a SQL. Or, yeah.
Cool. Any more questions? Oh,
I'm okay, yeah, thank you.
oh, okay.
So, I remember you mentioned about the postcode and the society data sets. So I'm not really sure, do you have any link between two of them? That is my first question. And my second question is, you mentioned about SORE, SORE, to double check data quality.
Soda core.
Yeah. And I'm not really sure, do you have any like API public so I can extract the data sets from like where you already collect all of this and clean and yeah, is this
We don't.
available right now?
We don't make available our input and output data, but
Yeah.
the Soda core library. Soda is like a lot of these things where they created like some library and then they had to commercialize it. So there's like an open source version of it and like a commercial version. And I use the open source version.
Yeah, so but right now you don't have any API public for like
Public
for
API.
anyone.
I don't. We EDINA we don't. No.
Okay. And
But the Solar Core library is free to use.
Do you have any suggestion if I'm interested about this or where I can find the data source?
The UK Data Service itself has lots of public accessible social and economic data sets.
Yeah.
So if you Google the UK Data Service,
Okay, yeah. Thank you.
Anyone else get any other questions? Oh, two more. Here we go.
I can share it. No?
You go first.
Hello, this is very quick question. You were mentioning using you mentioned livestock as a use case for that. Is it mainly for measuring population, or is there any other data that could be gleaned from?
for the ag census, it's just mapping like sort of livestock and crops and stuff.
Cool.
Just to show change over time and stuff.
Just curious.
The data's limited because it is at 2 kilometres or 5 or 10, so it's quite coarse. And
I had a question about the disclosure bit that you're doing.
yeah.
So are you, the grouping, are you doing it dynamically, or are you kind of rising up to the level where you have at least more than 1 point per raster?
We're just grouping, so from the 250 metre cells to 2 kilometre cells, or 5 kilometres, 10 or 20 kilometre cells.
Are you not doing any checks on at which point does it make sense to raise to?
We have to cite for each of the people who provide the data, so that's DEFRA or RESAS in Scotland or Government Wales. They provide us with a spreadsheet that lists each variable at what level of geography it's available at. So they've done that for us and told us you must provide this data at this level maximum,
Got it.
or we'll come in and take your data away from you. So we had to implement what they told us, basically. Yeah.
Cool. Anyone get any other questions? No? Okay, thanks for that.
Thank you.
Round of applause there.